Well, I have certainly enjoyed the last couple of days so far. And while we changed our agenda a little bit, the next three talks I think are all extremely interesting and are directly slated because of the feedback that we have had from our industry partners that come here, they enjoy the panel discussions, they enjoy the keynotes, they enjoy the poster sessions, but they've requested over the last year or so that they would love to see more Purdue initiatives and more Purdue research highlighted. So with that, we sought out to find some interesting projects that show not just great promise, but mature research that looks like it could be game changer and really assist industry within this area. That is extremely fitting for this next presentation, who is from one of our CERIAS affiliated faculty members, Sunil Prabhakar. Sunil, in addition to being a faculty member affiliated with CERIAS and in our computer science department, Sunil is also the department head of computer science. And I got to tell you, it's wonderful. Our computer science department is a great department, very broad as you expect in its focus across computer science. But to have a department head whose focus includes security is very beneficial to CERIAS. Right now they're going through in faculty recruitment for next year. And it's always nice to have somebody who understands security when we're looking to add that expertise. One of our new hires is in the audience. He actually had to register under his grad school address because he is not yet formal, but we have a new faculty member, Jeremiah. I'm glad you're with us, and we look forward to highlighting you as a faculty member next year. So this next talk really came about is that one of our partners, SRC, originally Syracuse Research Corporation, had given us a couple of topic areas they wanted to learn on. And I knew that Sunil's research fit this area. And I asked him to present. And it's been a couple of years since I'd seen him present his research. And I remarked afterwards and said, it's really matured since the last time I heard this. And he had shared that, yeah, we're ready. If we wanted to turn this to a product, we could. And so I said, well, this fits exactly with what our partners have asked for, is to see mature research, not something that, hey, if this works, it's going to be a really cool idea. But look, we have shown that this can work and this could be implemented. So with that, Sunil.
Thanks, Joel. Am I audible in the back? Thank you. As Joel said, I'm going to be talking about something that we've been working on for over 2 years now. We're at the point where I think it's almost productizable. So I like to use the tagline, fidelity without trust. But essentially what we're talking about is providing mechanisms by which we could increase the trustworthiness of data that we are retrieving from a server without necessarily having to trust that server in order to ensure that the data is trustworthy. And this is joint work with my PhD student who's now finished and is at Google, Rohit Jain. So a lot of the data that we deal with often sits in a database, and often those are relational databases. So that's going to be the focus of this particular piece of work, is getting trustworthy data out of a relational database. And just about every organization that has any reasonable amount of data to deal with will often store data in an Oracle or a DB2 or SQL Server database. Now, these databases are complicated pieces of software. They manage very large volumes of data with thousands of transactions, constantly updating the data, so they're constantly in a state of flux. And we trust the data that come from a database or that are hosted in a database because we trust, one, the software itself, we trust the hardware, and we trust the environment in which that database is currently being hosted. So this notion of trust is quite strong in our reliability in our belief in the trustworthiness of the data that comes from it. And even within the database system software itself, the trustworthiness of the data, the integrity or the asset properties, as they're often referred to, it relies upon the notion of the faithful executions of transactions following these asset properties. Right. So let's turn for a moment to the situation where we may not necessarily fully trust the database server. And by that, I'm using that term very generally. It could be the software, the hardware, the DBA, or the hosting, cloud service provider perhaps, but any such environment where we don't necessarily have 100% faith in what's going on in the database. So this could be either because we've put our data out into the cloud because we're deciding to outsource our database services, or we might be concerned about insider attacks. Someone with authority to make changes is making changes that we may not necessarily want to take place to the database, but because of the scale and the volume and the velocity with which changes take place, it may be hard to track. It could also be because we might have accidental modifications, and we might want to be able to detect those. So all of these I'm sort of rolling together into this notion of some degree of lack of trust on what's going on with your data. So the question that we're trying to address in this work is, can we still trust the data that come from in response to a query, or the data that are hosted in the database, make sure that this data is untampered. And I'll define what I mean by tampering in a minute. But essentially, if we treat, for example, if you go back to the notion of databases as they are today, we trust the value of a piece of data in the database to be correct as long as that database system faithfully executes only authorized transactions in the manner that, in the order in which we submit those, or we reported that they were executed. So that's all we really want to achieve. So the goal here is very, very simple, very narrow, I admit that. But essentially we're trying to say is, can we make sure that transactions are being faithfully executed on some database server somewhere without having to trust what's going on at the server, and can we validate that? And in terms of correct execution, I'm going to be very precise. We want to be assured that any value in the database system reflects what should have been a correct value. And by correct, I mean a value that would result from a faithful execution of all the transactions if we fully trusted, and we should be trusting that database. Also, whenever we retrieve data from the database, are we getting all the relative, all the values that are relevant to our query? That means we're not getting to see a part of the answer, but the entire answer. And finally, of course, importantly, and this is the piece that I think is really where this work makes a contribution, is if changes are being made to the database as part of the legitimate operations of your enterprise or of the database, are those changes being faithfully executed? Is this too close? All right, sorry about that. And also, it would be nice to know who's been modifying the data and how is that data being modified. So these are the kind of questions we want to answer without requiring trust of the database to get at those answers. So why would you doubt, let's just focus for a moment on the outsourcing service. Why would you doubt that? It's not good business practice for an outsourcing or a cloud service provider to be messing around with your data. But it could be that they get attacked by a hacker. Exposing the fact that they were attacked may not be good business practice either, right? No, it would be a bad business practice, but it may be a decision they make that is better off that they hide the fact that they were hacked. Secondly, they could make inadvertent changes and may not want to own up to them, or may have some other problems that may lead to that. So before we talk about our solution, let's just briefly look at what you could do today to protect yourself against this scenario. Right, so essentially the solutions that are available today, as far as I know, there may be better solutions out there, but right now essentially you sign an agreement with your cloud service provider, and of course you have the recourse to prosecute if something goes wrong. But when you're dealing with terabytes or exabytes of data with tens of thousands of legal transactions, modifying them all the time, and the state of the database constantly being in a flux, it's really hard for you to even know that something has gone wrong, right? So it's not necessarily an easy question to answer. Even if you suspected that something has gone wrong, let's say you do know that this number is not what it should be, how would you go about proving in code that this is the fault of your service provider, right? And that's kind of the question we're trying to get at that. And of course, if you're dealing with a situation where the data is on your own servers with insider threats or hackers attacking your own servers, there's really nobody for you to sue at that point in time, right? So can we avoid some of these current problems? So what we're proposing here is to try and reduce the level of trust that you need to have of this entity holding your data or processing your transactions while still getting guarantees about the fidelity of that data, right? So in particular, what we're trying to answer is the question is if it is possible to establish the authenticity and the integrity of the data, and of course of the answers to the queries that you run against this database without having direct control over that system. Right? Okay, and I will very openly declare that this is not an all-encompassing solution, not intended to be in any way. It's just a small first step, and I think we make some progress, and there's still a lot of open questions. And I will try to point out some of the limitations of this work as I go through the talk. So if your data don't change, if you're dealing, for example, with the US Census data from a prior year, and that the government wants to host those in a server and allow people to run queries against that while being assured that nothing gets tampered with the data, that's an easier problem to solve, and it's one that's been solved a while ago. And so we're not going to be worried about that. I will present the pieces of that solution to that problem because that's what we build upon. But I think the real challenge comes when the data undergo legal changes. And there are two ways you could handle legal changes. One is that you have a central authority that blesses and vets every single change. And if that's the case, then again the problem is not very hard. For example, if the Census Bureau discovers some errors in their data, they could change those, make those corrections, and then again post the data, make it available. That sort of situation is not very hard to handle. The difficult part is the kind of data where you have a big database that multiple authorized users are able to not only access for getting answers, but also to make changes to. And that's all happening concurrently without necessarily any control on who runs what transaction at what time. That's the muck that we are trying to get a handle on, make sure that that sort of chaos is being faithfully hosted by this database system. So in particular, we want to ensure the correctness of every value with respect to all these ongoing transactions, the completeness of any answer that you get back, and of course the consistency with regards to updates that are being made to the database. And somewhere in that is buried the notion of freshness. You don't want to see stale data because that's really not correct. So another way of looking at it, we want to make sure that the database gives us the truth, the whole truth, and nothing but the truth. Right? Okay, so here's a cartoon sort of laying out the different players in this game. So we'll have in blue the good entities. Carol is a authorized client of the database. We have the database itself. We're going to assume it's sitting out in the cloud. That's my little cartoon to show that. And an example database, what I'll use is one that simply records the names of suspects and their last known locations. So we have John and Jane Doe in New York and John Smith in California. And then we'll have in red the malicious entities, Mallory, who will attempt to try to make unauthorized changes to this database. So when I say correctness, here's exactly what I mean. So if Carol were to ask this question of the database, who are all the suspects in New York? And the database comes back saying Ivan Innocent is in New York. If Carol suspects this, and this is one of the limitations of this approach, that the database could come back saying Ivan Innocent and nothing would be flagged until Carol has a suspicion. But if Carol does suspect the validity of that answer, then essentially she can query or challenge the server to prove that Ivan Innocent actually was in New York in the database, and that reflects the current legal state of the database. Right? So in other words, the database should not be able to invent values that are not consistent with the current state. Completeness is, again, if she asks the same question, and in this case gets the answer John Doe. Certainly John Doe, I'm sorry, this font is really bad, you can't read it, but John and Jane Doe are in New York right now. So John Doe is a legal answer to this question, but it's not the full answer because Jane Doe should also be part of the answer. And again, if Carol suspects that, she should be able to validate that. Right? So in an ideal world, we would like a flag to go up whenever the answer is not consistent, but that's not something this solution provides. So in terms of consistency, consider a situation where an authorized user, Candy, learns that one of the, let's say Jane Doe, has now moved from New York to California. She makes a legal update to the database and changes that value. After that, if Carol asks the same question, in this case, the answer that earlier was correct is no longer correct and should, of course, not pass the test in case Carol challenges that answer. Right? So we want freshness with regard to the latest updates. And similarly, if Mallory makes an unauthorized change and then Carol runs this query, again, the update is reflects an unauthorized transaction, we should be able to catch the fact that an unauthorized transaction has sneaked in somewhere. Okay. All right, so those are the scenarios we're trying to deal with, and here's the key idea of the solution. So we're basically going to use authentication structures and involve the parties in a small protocol every time a query is executed, either for retrieving data or for updating data. And the server is going to have the responsibility of maintaining these data structures and all the necessary pieces of information in order to prove the correctness, the completeness, correctness, or consistency of any database answer that it provides. So that's the idea, and we want to make it impossible for this database server to fake any value, right? So we don't want, if this server has any sort of behavior that is not consistent with faithful hosting of their transactions, we should be able to catch the entity. That's the basic idea, okay? So here's how it works. In the beginning, Alice is the owner of the data. So this could be the US Census Bureau in that example earlier, but she starts with her database in a state that she's happy with. This is a consistent state. This could be a completely empty database which she could trust, and then everything gets added afterward. But what Alice does is that she computes this data structure, which is essentially a Merkle hash tree. So if you're familiar with Bitcoin, it's almost the same type of protocol. So she builds on every single attribute a Merkle hash tree and saves the root of the hash. And what she does is she saves that one hash value, which is 256 bits if it's SHA-256, or whatever your hashing function you were using. But one number is all she needs to save somewhere securely, right? And after this point, she will then put the database out into the cloud, make it available for Bob, who is the cloud, to be able to host this data and start serving queries for access or updates. Bob, before he opens up shop and makes the database available, would also go through the same step, compute the same hash functions, compute that one number, and the two of them need to agree that their initial numbers are the same. And after that point, Bob is open for business. So now down the road, when a Carol asks a question, she asks a query, she gets some sort of answer back. If she doubts it, and here's another limitation of this work, is that she has to explicitly request a validation, but she could request validation on every single transaction. That's perfectly fine, and she could go back 50 years and say, let's validate that transaction 50 years ago, if that's the arrangement. The downside to that, of course, Bob has to maintain enough data to go back 50 years, right? But at least the protocol allows you to go back arbitrarily in time. So if she suspects this or has any doubt, she will challenge Bob to prove the validity of that answer. And then she gets some pieces of data, and I can go through details if we have time. But then she computes a number and then checks that number against what's stored at Alice. And this has to be secure so that she doesn't get faked by some other entity pretending to give her that number. But as long as those numbers match, she is assured that the answers are correct and consistent. Right? So that's basically the idea of how the protocol works. So after checking that number, she knows that. Okay. When an update happens, if Candy updates any data, what happens, of course, is some confirmation goes back to her that her transaction has been processed. But at the same time, now we've got a change in that overall number, and that number is communicated over to this entity Alice, and Alice could outsource that to a trusted third party, this activity. All that trusted server needs to do is maintain a chain of these values as they move from one to the other in response to each transaction's update. If you wanted to reduce that burden, you could lump together, maybe 10,000 transactions get lumped together and then one notification goes out. That just increases your burden when you're trying to validate. So instead of validating a single transaction, you'd have to validate the group of 10,000 that it belongs to. Right. Okay, and then of course the same situation if Candy has any doubt about not only the values that her transaction read, but about the updates that her transaction should have installed into the database. She wants to be sure that those are the only changes that her transaction effected into the database. Then she can actually run the same protocol again, get some bits of data from the sibling roots, sibling hashes along that Merkle hash tree for each attribute modified, and be able to compute and check that this chain is maintained. There is a little bit of burden on Alice. Alice does have to do a little bit more than just keep this chain. There's a notion of sequence IDs and other details which prevent Bob from dropping transactions and adding transactions. But I can go into that if anyone's interested, and certainly it's all in our paper. Okay, so with this simple protocol, what we get essentially is that now any entity, Alice or Carol or Candy, can validate any given transaction either the latest one or anyone back in past in time, without having to trust Bob whatsoever, right? So there's zero trust required. Now, of course, you could get a denial of service attack very easily. If Bob fails the test each time, then you're going nowhere. But that's not part of what we're trying to address here. We're assuming Bob is going to play nice and wants to host your data, and will try his level best to provide high quality service. But Bob cannot pretend to be doing the right thing when he's not. So he will definitely get caught, right? This task that Alice is performing could be outsourced. It's much easier than trusting somebody to maintain a chain of hashes than to trust in the execution of an entire database system. And of course, the nice thing is that multiple independent clients can at the same time run concurrent transactions, which is what databases give you. And at any given point in time, there is no consistent state. I mean, it's all a big mix of half-baked transactions running at any given point in time. But since we are piggybacking on the notion of transaction commitment, we can handle essentially the sequence of updates to the consistent state of the database. Okay, so I already talked about the motivation. So certainly this protocol can help guarantee the authenticity and integrity of data that's not necessarily in an environment that you fully trust. But on the flip side, this solution for free gives indemnity to Bob. Right? So if Bob is behaving well, it prevents a malicious client from falsely implicating Bob for having misbehaved with the data. Right? So it protects Bob if Bob is honest. Okay. Just to clarify, how are we doing for time? Okay. So just to clarify, the verification is done on demand. There isn't a flag that goes up whenever Bob does something that he should not have done. But you have the power to go back and validate any transaction back in time. So we expect in practice, you might have a higher rate of validation when your trust level is a little bit lower, but you can ratchet back. But it's also possible for you not to validate a transaction at the time it's executed, but wait and just have at random pick transactions back in time to challenge Bob independently. And that can happen on the side. It does not have to impact your online transaction processing. Right? So it doesn't have the overhead that you might normally have. Okay, I think I already covered that. An important caveat, this solution is orthogonal to the notion of privacy. We're not trying to protect the privacy of the data at all. If you did want to have privacy and you chose to use encryption to achieve that, the solutions work directly with that. The only limitation is, of course, if you do not have order-preserving encryption, then you can't do range queries and you can't get the guarantees of completeness that I talked about. But if you have order-preserving encryption, you get those automatically. We also do not keep track of who is accessing the data, right? So this solution provides no information about that. But we do have an extension where we use encryption and a special kind of encryption that allows you to essentially be assured that this server is enforcing access control rights over the data without, again, trusting the database system. Again, essentially the way we do that is just access to keys, and it's a key management problem. Okay, a side effect, again, is that you get secure, provable provenance of all your data. Every single change, you know exactly why it took place, who authorized it, and what exact changes were applied. Okay. So just to clarify, we have some assumptions here. We do require a trusted entity that's maintaining this chain of the hash values. If that's compromised, of course, this breaks down. We also assume that you're using unbreakable one-way hashing. We're assuming digital signatures are unbreakable. If you can break any of those, all of these guarantees go away. And there's one minor piece here which I've sort of swept under the rug, but it's an important piece, and that is when you have an update transaction, what you're going to get from the validation process is you're going to say, when this transaction ran, it read these values, and I can verify to you that the values came from this consistent state. And after it ran, all its changes were reflected in the next consistent state. That's the level of verification you get. So you do need some sort of mechanism which takes the transaction, looks at the values read, and then make sure that that's consistent. For example, if your transaction was transferring funds from one account to the other, you would get to know the 2 account balances before and after your transaction, and you just need to make sure that that change is a valid change for that transaction. That's not automatic, but for most database transactions, that's easy to do. And of course, we assume that the server can authenticate users and protect itself. Okay. So where we are today, we've actually implemented this on top of Oracle and Postgres, and it turns out to be relatively easy to do. We just have a wrapper around. We rewrite the queries. Through query rewriting and creating shadow tables of every table that we have, we are able to essentially implement this very easily. The overhead is an issue. We have, at this moment, a very, very simple implementation with no changes to the internal code of Postgres, and certainly we don't have access to internal code for Oracle. But what we see is that if you're not validating transactions all the time, the overhead is very small. It's just validation that takes time. And validation actually can be offloaded to a side entity. It does not have to be conducted by your online transaction processing system. So you can actually get decent performance. We're also extending beyond relational to other object-oriented databases and XML. So I'll stop there and take questions.